Welcome to this explainer. Today we're taking something that seems, honestly, incredibly simple, just putting an object on a scale to see how heavy it is, and we're going to reveal the absolutely mind-bending science behind it. We're taking a simple 200-gram weight on a journey across fundamental physics, planetary mechanics, and some extreme laboratory precision. It's going to be a fun ride, so let's dive right in. Here's our quick roadmap for today. We'll start with mass versus weight, look at the gravity glitch, and talk about redefining the kilogram. Then we'll get practical with prepping for calibration, walk through the core tests, and finally wrap up by embracing uncertainty. Section 1. Mass, weight, and gravity. To really set the stage here and understand calibration, we kind of have to start with a crazy thought experiment. Ask yourself, what would actually happen if gravity just suddenly vanished? I mean, we completely take it for granted, right? But it's literally the invisible anchor of our entire reality. Without it, the whole concept of a balanced scale wouldn't even exist. Just imagine the utter chaos. Anything not bolted down would simply fall upwards and float away. There's no way we'd be able to stop moving. Ships, buildings, us, we'd all just be completely adrift. It was actually Sir Isaac Newton, way back in the 17th century, who first brought mathematical order to all this chaos. He defined the laws of motion and gravitation that, believe it or not, we still use to calibrate the most advanced digital scales today. So right off the bat, the absolute most crucial point we've got to establish is the difference between mass and weight. They are absolutely not the same thing. Mass, which we measure in kilograms, is the constant amount of matter in an object. A 1 kilogram mass is exactly the same here on Earth as it is floating out in deep space or sitting on the surface of Mars. But weight, measured in newtons, that's the actual pull of gravity on that mass. And as you'll see, weight changes depending on where you are in the universe. Section 2. Gravity's effect on weighing. Okay, so how does planetary physics wreak havoc on practical lab measurements right here on Earth? Well, our planet isn't a perfect sphere, right? It's an ellipse. It bulges at the equator and flattens out at the poles. Because of that, and because of variations in altitude, gravity just isn't uniform. Take a look at Antalya, a coastal city that's essentially right at sea level. It has a higher gravity value because it's slightly closer to the Earth's center of mass, especially compared to a city like Konya, which sits way up high, over 1,000 meters in altitude. Now you might be wondering, why does this actually matter? Well, let me hit you with a pretty surprising number. 81.6 milligrams. If you take a super-sensitive laboratory balance, meticulously calibrate it down in Antalya with a 200-gram mass, and when you pack up that exact same scale and that exact same mass and drive them up to Konya, the scale's going to read wrong. Because the gravity is weaker up in Konya, the scale will show a massive 81.6 milligram error. For an analytical balance with a 0.1 milligram resolution, an 81.6 milligram swing is an absolute disaster. It's a real game changer. This is exactly why a scale must always be calibrated in the specific location where it's actually going to be used. Section 3, redefining the kilogram. So if gravity is this variable depending on where we're standing, and physical objects degrade over time, how on earth do we establish a universal standard for measuring mass? Well, the answer to that has actually changed over time. Back in the late 18th century, a kilogram was defined as the mass of 1 cubic decimeter of water. Then, by 1901, the world upgraded to a literal piece of metal, a specific platinum iridium cylinder locked away in a vault in France. But here's the catch. Metal can lose microscopic amounts of matter over time, or even gain it through contamination. So on May 20, 2019, the scientific community completely changed the game. We arrived at the new kilogram. It's now defined not by some physical object, but by a fundamental, completely unchangeable truth of the universe, the Planck constant. This was a massive, absolutely crucial revolution in metrology. It completely freed nations from having to rely on that one single piece of metal locked in a French vault. Now, any laboratory out there with the right, highly advanced equipment, like a kibble balance, can realize the exact mass of a kilogram just by referencing the fabric of quantum physics itself. How cool is that? Moving on to Section 4, preparing for calibration. All right, with the theoretical physics out of the way, how do we actually apply these universal truths in the lab? Well, before a single test weight even touches a scale, the preparation has to be flawless. You can't just plug a high-resolution balance into the wall and start working. Electronics generate heat, right? And heat changes electrical resistance and mechanics. So high-resolution balances might literally need to warm up for up to 12 hours just to stabilize. Plus, the reference weights you use must be left in the room to perfectly match the ambient temperature. If you put a cold weight on a warm scale, it creates these tiny little air currents, convection, that literally push up or pull down on the scale, totally ruining your measurement. And speaking of those reference weights, you've got to handle them with extreme care. I mean, you must never, ever touch them with your bare hands. The microscopic oils, sweat, and dead skin cells on your fingers, they actually have mass. If you touch a reference weight, you've essentially just glued your dead skin right to it, making it heavier and completely throwing off its calibration. No way you want that. They must only be handled with specialized tweezers or really clean, lint-free gloves. Section 5. Core calibration tests. Okay, so once our environment is prepped and our weights are perfectly acclimatized, we move to the core procedures. There's a very specific roadmap for this. We perform 3 main tests: repeatability, eccentricity, and linearity. Let's look at how we transition from all that theoretical physics into highly structured, hands-on lab execution. First up on the list is repeatability. It's kind of exactly what it sounds like. If you put a weight on a scale, take it off, and put it right back on, does it give you the exact same number every single time? For this test, a metrologist will load a weight onto the center of the pan, typically at least 5 times, zeroing out the scale in between. If the scale's internal mechanics are sticking or degrading even a tiny bit, this test is going to catch that inconsistency for sure. Next is the eccentricity test, which is sometimes called the corner load test. Now, in a perfect world, a user places their sample dead center on the weighing pan every time. But in reality, people are sloppy. We place flasks off to the side all the time. So we test for this by taking a weight, usually about 1/3 of the scale's maximum capacity, and placing it right in the center, and then sequentially on all 4 corners or quadrants of the pan. The scale must read the exact same weight regardless of where that load is sitting. And the final major hurdle is linearity. Just because a scale is perfectly accurate at 10 grams, it definitely doesn't mean it's perfectly accurate at 100 grams. Linearity testing involves checking the scale across its entire operating range. Metrologists will use a 5-point or sometimes even an 11-point test. They'll start at 0, then go to 25% capacity, 50%, 75%, all the way up to max capacity. This ensures the electronic response of the scale is a perfectly straight line, meaning it's accurate at every possible point. Section 6. Understanding measurement uncertainty. Finally, we need to confront a fascinating and honestly somewhat humbling truth in science. No measurement is ever 100% perfect. Whenever a lab issues a calibration certificate, the whole shebang comes with an uncertainty value. But we shouldn't frame these variables as just tedious math. It's more like the chaotic nature of the universe that we just have to mathematically account for. Think about it. The digital display rounds numbers up or down. That pristine reference mass, it might have drifted slightly since its last calibration. Even the air in the room exerts a buoyancy force on the weight, pushing it up slightly, exactly like water pushes up a boat. And as we mentioned earlier, tiny temperature differences create convection currents. All of these minute errors are calculated, combined, and openly stated, so we know exactly how close to the true value we really are. So what does this all mean? Is any measurement truly absolutely perfect? Well, the answer is no. Absolute perfection is practically impossible in a universe completely full of shifting variables. But by understanding the physics of gravity, utilizing the quantum constants of the universe, and mastering these rigorous calibration equations, we get incredibly, breathtakingly close to the absolute truth. Thank you for joining me on this explainer. I really hope you never look at a simple scale the same way again.